Alright, so in this video we're going to discuss nuclear binding energy and mass defect, two crucial concepts in nuclear physics that you'll need to understand for the MCAT. We're going to dive into the definitions, the significance, and some of the calculations and practice problems of these concepts. Let's get started. Nuclear binding energy is the energy required to disassemble a nucleus into its component protons and neutrons. It's a measure of the stability of a nucleus. The greater the binding energy per nucleon, the more stable the nucleus. Binding energy indicates how strong the nucleons, protons and neutrons, are held together. This energy comes from the strong nuclear force, which overcomes the electrostatic repulsion between the positively charged protons. Binding energy can be calculated using Einstein's famous equation E equals mc squared. Here, E is energy, m is mass, and c is the speed of light. This equation shows the relationship between mass and energy, indicating that mass can be converted into energy, and vice versa. Mass defect is the difference between the mass of a nucleus and the sum of the masses of its individual protons and neutrons. When a nucleus forms protons and neutrons, some mass is converted into binding energy, which is why the nucleus's mass is less than the sum of its parts. Here, delta M is the mass defect, Z is the number of protons, MP is the mass of a proton, N is the number of neutrons, Mn is the mass of a neutron, and M nucleus is the mass of the nucleus. It's important to note that this equation is likely to not be tested on the MCAT, and if it is, it will be provided to you. The most important equation that we're going to be talking about today is Einstein's equation. So to calculate the nuclear binding energy, we use the equation E equals mc squared. Let's go through an example with easier numbers typical for MCAT calculations. Suppose the mass defect of nucleus is 0.03 atomic mass units. Converting this mass defect into energy, 1 atomic mass unit, or AMU, is equal to about 931.5. So if we take that and multiply it by the 0.03, we get roughly 30 MeV. So rounding down to significant figures, the nuclear binding energy is approximately 28. The binding energy per nucleon determines the stability of a nucleus. Generally, nuclei with the binding energy per nucleon around 8 MeV are very stable. Iron 56, for instance, has one of the highest binding energies per nucleon, making it extremely stable. In nuclear reactions such as fission and fusion, changes in nuclear binding energy explain the large amounts of energy released. In fission, heavy nuclei split into smaller nuclei, releasing energy. In fusion, light nuclei combine to form a heavier nucleus, also releasing energy. Understanding the strong nuclear force is crucial. This force holds nucleons together within the nucleus, overcoming repulsive electrostatic forces between protons. It acts over very short distances, making it extremely powerful. The concept of mass energy equivalence, given by E equals mc squared, shows that mass can be converted into energy and vice versa. This principle is key to understanding nuclear reactions and the energy released during these processes. The binding energy per nucleon curve is crucial for understanding nuclear stability. It shows that nuclei lighter than iron release energy through fusion, while nuclei heavier than iron release energy through fission. Iron 56 sits at the peak of the curve, indicating its high stability. This is why it doesn't undergo fusion or fission under normal conditions. In nuclear fission, a heavy nucleus splits into smaller nuclei, releasing energy. This process is used in nuclear reactors and atomic bombs. In nuclear fusion, light nuclei combine to form a heavier nucleus, releasing energy. This process powers stars, including our sun, and holds potential for future clean energy sources. Now, let's test your understanding with a few practice questions. These are the types of questions you might encounter on the MCAT. A nucleus has a mass defect of 0.025. What is the binding energy in mega electron volts? The correct answer is B, 23.3. So if we use E equals mc squared, converting the mass defect to energy, we have 1 AMU is equal to 931.5 mega electron volts. We then can take this and multiply it by the atomic mass unit, 0.025, to get 23. In a nuclear fusion reaction, two deuterium nuclei, each with 1 proton and 1 neutron, combine to form a helium-3 nucleus, 2 protons and 1 neutron. What can be said about the mass defect and binding energy? A. The mass defect is negative and energy is absorbed. B. The mass defect is positive and energy is absorbed. C. The mass defect is negative and energy is released. Or D. the mass defect is positive and energy is released. So as we can tell, this is a common and very classic example of process of elimination, and it's called a 2x2 question, meaning that if you have one part of the question right, you're able to essentially eliminate two answers. For example, we can first figure out, is energy being released or is it being absorbed? Or we can figure out if the mass defect is negative or positive. The easiest one is probably the energy. In this case, in terms of the actual energy being released, it is going to be released because this is a fusion reaction. And because we're then able to show the energy released, and as we said, in fusion and fission reactions, energy is released in both. So effectively, that eliminates A and B. So now we just have to figure out, is the mass defect negative or is it positive? In fusion reactions, the combined mass of the product is less than the sum of the reactants' masses, and therefore, this makes the mass defect positive. So these questions are going to help reinforce the concept of nuclear binding energy and mass defect, and understanding these principles is crucial for tackling the MCAT. To excel on the MCAT, it's crucial to master the following key points: understanding the concept of nuclear binding energy and its significance to nuclear stability, being able to calculate mass defect and convert it to binding energy using E equals mc squared, recognizing the implications of binding energy in nuclear reactions such as fission and fusion, and applying this knowledge to solve MCAT-style practice questions. So in summary, nuclear binding energy and mass defect are fundamental concepts in nuclear physics that are essential for understanding nuclear stability and reactions. By mastering these topics, you'll be well prepared for the MCAT. And if you found this video, don't forget to like, comment, and subscribe to our channel for more MCAT and USMLE prep content. If you're in the app, please make sure to drop a like on the video and leave a comment if you have any questions. Your support encourages us to continue creating these videos. Thank you and good luck studying.